Hey everybody, in this lesson I'm going to define and explain a concept known as half-life, and we're also going to take a look at how to solve some simple mathematical problems related to half-life, in particular time and nuclear decay processes. So let's get started by remembering that when you have unstable atoms, they will decay. That means they are breaking down and turning into different smaller pieces. And a good example of that would be something like this potassium 142 or potassium 42. It's an unstable atom, which means it doesn't stay potassium, right? It's going to try to turn into other things that are stable. And one of the ways that it does it is by releasing a beta particle and turning into calcium 42. So that is the beta decay process that potassium 42 undergoes in this lesson. And when you're thinking about half-life, what you're really thinking about is how long it takes for this process to happen. Right? So half-life is all about time. We're going to keep going with this potassium 42 example, and you can see that I have an imaginary brick, let's say, that is made completely of potassium 42, and it's an 80-gram block. And we're going to use that to sort of understand what half-life is telling us. I'm going to hold off on a definition of half-life because it's the type of thing, it's fairly simple, and it's probably better if you see how it works instead. So we're just going to watch this block, this 80-gram block of potassium 42, and see what happens to it over time, and in doing so, sort of discovering what half-life is. The first row that we're going to fill out to help keep track of how this block changes is the elapsed time. And we're going to first define that at 0 minutes, so essentially the very beginning of my experiment, there's 80 grams of potassium 42. Obviously, because nothing has happened yet, right? This is the very beginning. That means nothing has decayed, right? No, we haven't lost any potassium 42 yet. And in terms of percentages, 100% of the potassium 42 is still there. And that means 0% has decayed. So just to point out one important difference in these last 4 rows, these two and these two are saying the same thing. It's just that the first set is doing it with the masses, and this second set is doing it with percentages, but essentially you're seeing the exact same thing. The next thing I'm going to provide is a piece of information, and that information is the half-life of potassium 42. This number happens to be 25 minutes. You don't have to worry about how to know that. This is something you would be provided with. And so I'm telling you, potassium 42's half-life is 25 minutes. So to understand what this means, what we're going to do is just literally start waiting, right? I'm going to wait 25 minutes later from that initial 0 minute moment. And we're going to start to see what happens with my potassium 42. So that means my elapsed time now is 25 minutes has passed. The block that was 80 grams, made of fully 80 grams of potassium 42, now changes, and the amount of potassium 42 splits in half to just 40 grams of potassium 42. The whole block's mass doesn't change. The entire block's mass is still 80 grams. It's just that, the potassium 42 is changing into something else, right? So only 40 grams of potassium 42 is left. The other 40 grams has now decayed and turned into this product, this calcium 42. So that means after 25 minutes, only 40 grams is left. The other 40 has decayed. In terms of percentages, that means we've lost 50% of the original 80 grams and 50% has turned into the calcium. So that's what would happen after one 25-minute time period. Now I'm going to wait another 25-minute time period and see what happens again. So if you watch the masses on the right-hand side, what was 40 grams of potassium 42 now splits in half again to just 20 grams. The entire block still weighs 80 total. It just means that now there's 60 grams of calcium in that block. So from the 25, now 50 total minutes, where we split to 40 grams and now 20 grams, I now have 60 grams of potassium 42 that has decayed and turned into calcium. In terms of percentages, I've only got 25% of the original 80 grams left. 75% has decayed. And by now you should probably already have a pretty good idea about what half-life actually is. We're going to do one more of these splits just to make sure you can see the patterns developing here. So we're waiting an additional 25 minutes on top of the 50 that just happened. My 20 grams of potassium splits in half again to 10. That means 70 grams is now calcium. So almost this entire block is now calcium. So we've gone 25, 50, 75 total elapsed minutes. My mass is splitting from 40 to 20 to 10. That means 40 grams first of potassium had decayed into calcium. Then it was 60 grams decayed into calcium. Now it's 70 grams has decayed into calcium. In terms of percentages, first I lost 50%, now 25%, and finally 12.5% of that original potassium 42 is left. That means the other, larger majority here, what would that be? 87.5%, if my math is right, has decayed. And by now you should probably see what's going to happen. So let's just switch and fill out the very last column of this table. You also probably have a fairly solid working definition of what half-life is in your head. If you don't, let's clarify it officially together. Half-life is, first of all, time. It's the amount of time that is required for something to happen. And the something is for exactly half, hence the term half-life, for half of the nuclei in a sample to decay. And the column, or the row to really focus on here, is in red. And that really shows you what's happening. It literally splits in half, 80, 40, 20, 10, 5, every 25 minutes. And the 25 minutes is the half. So we're going to end this by just focusing on two things. The first is just letting everybody know that different elements and isotopes have different half-lives. If you took something that's relatively stable, like uranium-238, it's going to take 4.5 billion years for half of the isotopes in a sample to decay. So the more stable it is, the longer the half-life is going to be. And you could compare that to the other end of the spectrum, something like lithium-8, that is extremely unstable, and its half-life is like super teeny tiny fractions of a second. So there's a huge range of different half-lives that things have depending on how stable they are. It decays slowly, it's relatively stable. Some decay almost instantly, which means that they're made of very unstable nuclei. And we're going to end this whole thing looking at how to apply this idea to some simple mathematical examples. This first one says nitrogen-13 emits beta radiation with a half-life of 10 minutes. If you began with a 2-gram sample of nitrogen-13, how many grams would remain after 3 half-lives? I have another version of this table sort of set up that we can use because it's this type of table that you can almost always use to solve at least simple half-life questions. Just by starting back at 0. 0 elapsed time have passed, 0 half-lives have passed. You're always starting at 0. At that point 0, you've got your initial mass that you can fill out. In this case, it's 2 grams. And then just sort of remember what half-life is. It splits in halves every certain amount of time. So from 2 grams to 1 gram, 1 gram to 0.5 grams, 0.5 to 0.25, 0.25 to 0.125. And notice I did a whole bunch of those. I don't know really even what this question is asking me yet. I'm just sort of emphasizing what half-life is. It splits in half every half-life. Now this question doesn't even give the half-life. So as far as the elapsed time, I don't really know that because it doesn't tell me what the half-life is. All it wants to know is how many grams would remain after 3 half-lives have passed. So I've already got that answer in this table. Let's just find exactly where it is. So here would be after 1 half-life. This would be after 2. This would be after 3. So officially the answer to this question would be 0.25 grams of nitrogen-13 is left. Here's another example that says manganese-56 is a beta emitter with a half-life of 2.6 hours. What is the mass in a 1 milligram sample at the end of 10.4 hours? So remember, we always start at 0 half-lives, 0 elapsed time, with an initial mass in this case of 1 milligram. Before I even really comprehend the question, I'm just going to do a bunch of different half-lives to 0.5, to 0.25, to 0.125, to 0.0, think it's 0.625. That's all just in my head, so I might be a little bit off there. That's how I like to do these, and then go back and see what the answer what this question is actually asking for. So here we know the half-life is 2.6 hours. That means after one half-life, 2.6 hours has passed. After two half-lives, we've gone another 2.6 hours on top of this one for a total of 5.2. After three half-lives, another 2.6 hours has passed for a total of 7.8 hours. And another 2.6 hours has passed for four half-lives in a total of 10.4 hours. You could keep going if you wanted to, but if you go reread this question, we don't have to, because right here I've got my answer. It says, what is the mass of manganese-56 at the end of 10.4 hours? And that's where I'm at. So the official answer here would be 0.0625 milligrams. And we'll do one more example that's a little bit different. This one says, the mass of cobalt-60 in a sample is found to have decreased from 0.8 to 0.2 in a time period of 10.5 years. What is the half-life? So this one's a little different. This is asking me for the half-life itself. I'm still filling out the table the same way. Starting at 0, my initial mass, it says, is 0.8 grams. You can still split that in half, 0.4, 0.2, 0.1, 0.05, as many times as you wanted to. The twist here is that it's saying it goes from 0.8 grams to 0.2 grams. So that's a little unique in that to get from 0.8 to 0.2, that's not one half-life, that takes two half-lives. And that total time period is 10.5 years. And from this information, it's asking for the individual half-life. So what is each one of these jumps? That's where you would actually find the half-life itself. Since we know that 10.5 years is two of these half-lives, then you can just divide 10.5 by 2 to get 5.25 years as each individual half-life. Your final answer is 5.25 years. So that wraps it up for this lesson on half-life and solving simple half-life problems. Thanks a lot for watching.